physicists. Welcome to Standard 5.3. In this standard and in this video, we're going to focus on work and power. Before we jump in too far, though, I want to back up a little bit to kind of prep us for what we're going to do. So in Standard 5.2, we focused on a concept called conservation of energy. I write that as COE for short. Now, conservation of energy worked under this premise that the total energy in a system remained the same, right? We said that the total energy at A equals the total energy at B, and that's how we solved the problems. One piece that was really, really important to our kind of establishment of this was this idea of a closed system. And a closed system, as we said, is one in which there are no outside forces. So depending on how you define your system can include the Earth, in which case gravity is an inside force. It's not an external force acting on the system. And so therefore, as you have a roller coaster car going down a ramp or something like that, for example, you can still have energy conserved with our gravitational potential energy turning into kinetic energy as that cart is going down the ramp. Okay. So again, no outside forces are acting. And in that case, then we can say that the total energy at A equals the total energy at B, and therefore we can kind of solve these problems super easily. 5.3 is focused on the idea of what if it's not a closed system? So 5.3 really works under the premise of what if there is an outside force? So outside forces are allowed, outside forces are encouraged. This is where we're really digging into what an outside force will do to a system. So I'm going to say outside forces act on a system. And just a friendly reminder as you're kind of thinking through this, well, what's the system? Remember, the system is just all of the important things that you declare to be part of the story when you're doing your LOL charts. So you've got this first axis that tells you all of the information before, and then you've got that big circle in the middle. And that big circle is where you define your system. And we'll dig into that a little bit more later in this video, but I just wanted to kind of point out that that's really where that lives, okay? So in a closed system, no outside forces act, and the total energy has to be the same the whole time. If you have outside forces acting on a system, what does that do? Well, it means that you can add or remove energy from the system. Okay, so the way that we name this idea of adding or removing energy kind of depends on the situation, but there are two primary ways that we describe that. One is called work, and another one is called thermal energy. And like I said, there are lots of different ways to define that and kind of names to call them, but these are the ones that we're going to use this year. So what is work? That's a really good question. You have heard the term work plenty of times in your life, right? So you may think of it as something you have to do, something where you make money, something where, you know, your assignment, all of these different kinds of things can be thought of as work in the grand scheme of things. Work, as it relates to physics, has a very specific definition, and that's what we want to talk about right now. So work, as it's defined in physics, is a force acting over a distance. A force acting over a distance, okay? What does that look like? Well, work is marked with a capital letter W, okay? And we're saying that it's a force acting over a distance. Now, if you take a look in your textbook, or if you look on your equation sheet, I will tell you that the equation doesn't look exactly like this. Why not? Well, it's got this funny little thing in it. It says actually work is equal to force times distance times the cosine of the angle theta. Now, depending on your math background, you might freak out when you see that cosine theta because you're like, what in the world does that mean? I'm going to tell you another way that you can look at that same equation that to me makes it make a little bit more sense. I'm going to say work is equal to force times distance, where the force and the distance have to be acting in parallel to one another. So what does that really mean? Well, it means that if you are applying a force in this direction and you're moving an object in this direction, so your delta x or your displacement is in that direction, then there is work done on that object. Okay, and we're going to get into some examples of this in just a moment. Okay, if you have a force applied in this direction, but your displacement or your change in position is in that direction, what this means, because there is no component of this force in this direction, okay, that means that there is no work done. Okay, let's take one more example just to kind of break this down into what it really means. Let's say you have a force acting like this. Ooh, so now we've got forces at angles, right? And let's say that it's got a displacement in this direction, delta x, okay? What this definition says is that some of that force is doing work and some of it isn't. So I'm going to say there's some work done. How do I figure out how much? Because as a physicist, you're not just going to be like, yeah, it's some. We need to know how much. So there's some work. We're going to figure out how much it is. So you can do this one of two ways. You can either get an angle and find the cosine of that angle, and that's a legitimate way to do it. Or you can just look at the piece of the force that's acting in the same direction as that displacement. And really that cosine is doing the same thing. I just don't want you to get like all in a fluster there. The part of the force that we really care about is the part that I just highlighted in blue. So the work that's done is just that smaller piece of the force acting over that direction. Now, I don't imagine that we're going to have a lot of problems where we have to actually look at that angle, but from a conceptual perspective, that is a really, really important idea. Okay? Now, that's kind of the very basic definition of what work is, but it probably doesn't mean a lot yet. I'm going to define the units really quickly, and then we're going to do some examples that will hopefully help to solidify the understanding, okay? Last thing here before we move on to some examples is to talk about units, because whenever we introduce a new concept, we always want to include units in there. So the unit for force, well, work is equal to the unit for work, I misspoke there, is force times distance. Force is measured in newtons. Distance is measured in meters. Now, we looked at this a little bit before when we were talking about energy. A newton times a meter is a joule. Work is measured in joules as well, okay? Just like your energy is. We'll see why that is in just a minute. Okay, so let's take a look at a few examples. Now, I will tell you that I hope you're not coming to this video on an empty stomach, because for some reason, the examples that I've developed all have to do with food. So welcome to my world, and I hope that that's okay. Example one is about lifting a cheeseburger. And the reason that these examples kind of started to develop was because I was talking to somebody and realizing that a cheeseburger, which, you know, we kind of think about like how big is a cheeseburger? Well, it's like we think about like a quarter-pound cheeseburger. So a quarter pound, oh, hello, is about equal to 1 Newton. So the reason that I chose this is because then we can talk about it having a weight of 1 Newton, and that makes your life super, super easy. Okay, so I want you to imagine that you are sitting at a table and there is a plate in front of you and it's got a cheeseburger. Now, you might be lactose intolerant, so maybe it's just a hamburger. You might not eat meat, so maybe it's a veggie burger. Whatever kind of sandwich it is or meal it is, just roll with me here, okay? So we've got a cheeseburger. I'm going to go ahead and draw that cheeseburger here. And we'll go like this, and there's my cheeseburger, and we'll just call it good. So it's sitting on a plate, and it's just waiting to be eaten. Now, in order to eat it, what do you have to do? You're not going to put your head down and start just chowing down on it. That wouldn't be appropriate. No, no, no. You're going to lift it up, right? You're going to pick it up. And so in doing so, I'm going to draw this like a little bit later. So maybe here it's sitting in the air and maybe the plate was all the way down here now. So we've lifted it up some distance. Okay. We'll call that D. You might want to call it delta X, whatever makes your heart happy, but it's been lifted up some distance. And just for kicks so that we can get some values in here, let's say that you lift it up, oh, I don't know, maybe 40 centimeters. Depends on how tall you are, how tall the table is, all of those sorts of things. But we'll say 0.4 meters, okay? And let's look at the forces acting on this cheeseburger. We haven't drawn a free body diagram for a while, so let's do it. Well, the earth is pulling down, isn't it? I'm going to be lazy and just write that as FG, but we know that's the force of the earth on the cheeseburger. And then in order to lift the cheeseburger up, you have to apply a force that's at least as big as the force of gravity pulling down, right? Otherwise, it's not going to accelerate upwards or move in the upwards direction once it started moving. So we've got some sort of applied force, and that applied force, FA, has to be at least greater than or equal to FG, okay? So we're lifting that cheeseburger up all the way to our mouth. We're applying a force over a distance. My question is, are you doing any work? Well, we can figure that out now, can't we? So we're going to take a look. We know that work is equal to the force we apply times the distance we do, where the force and the distance have to be parallel to one another. All right, so I'm going to tell you that the applied force that we are doing, because I want to know how much work do you do when lifting the cheeseburger? So is done by you as you lift the cheeseburger. Well, you apply a force. I'm going to say that it's 1 Newton of force, okay? And you apply that force over 0.4 meters. So the amount of work that you do is 0.4 joules of work. So the calculation there is pretty darn easy. I want to dig in a little bit though and look at some other pieces that go with this. So here's the first one, just for kicks. Let's take a look at a graph, okay? A graph of force and distance. So I want you again to imagine that you're lifting that cheeseburger up. We said that the applied force that you're going to use to lift that cheeseburger up is going to be the same as the gravitational force. Now, if you are a stickler for the truth, then you might argue. So I'm going to say that this is the table and this is your mouth. Okay, so I know that that's kind of on the x-axis, which feels a little bit funny, but if you tip your head, then maybe it'll work here. Okay, and this is going to be the force of gravity, or the weight of my cheeseburger. Now, for most of the time that I lift this up, it's going to be a constant force that I apply. Again, the sticklers here are going to say, well, if you're going to get it to start moving, then you got to apply a little bit bigger force to get it to accelerate. I don't disagree. So there's going to be a little bit of something going on at the beginning. And then if you want the cheeseburger to stop it at your mouth and not just keep going up, 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 which would be kind of awkward. Again, we're talking, good manners here. Then we're going to have to apply a little bit smaller force at the end. The game is, though, friends, and this is where I want you to see this because it's so cool, okay? This little blip here and this little blip here kind of cancel each other out. And we can see, I think this is so neat, look at the graph, okay, that the force here times the distance here, the area under the curve is equal to the work done. How great is that? What? Are you going to have to use that a lot? No, but is it really awesome? Yes, indeed it is. The area under the curve of a force versus distance graph is work done. For my calculus and pre-calc friends, that might make your heart really happy. For my other friends, just appreciating being able to graph these things is pretty great as well. Okay, let's dig into this one a couple more ways. There's a lot to be seen here, friends. Okay, so I'm going to take a look at this bar chart as well. So same kind of thing that we did during 5.2. Let's take a look at the initial and final situations for my cheeseburger. Now, at the very beginning, my cheeseburger isn't moving, but I'm going to start it moving, It does not have very much gravitational potential energy if I decide, actually I'm going to make that, let's see if I can make it a little bit smaller here. If I set my h equals 0 where I want it to be. So let me set h equals 0 at an appropriate place, like, I don't know, maybe right there. Okay, then there is no gravitational potential energy. There's going to be no kinetic energy at the very beginning and no kinetic energy at the very end. Remember, we have those little blips that kind of get it to even out. So there's no kinetic energy at the beginning. There's no elastic involved, no thermal energy involved. I'm going to argue there's no energy involved at all at the beginning. What? Okay, but here, now let's look for a second. What was my system? My system is the cheeseburger. I'm just going to write that as CB. And maybe the earth, right? At the end, do I have any energy? Well, it's not moving, so there's no kinetic energy. There's no elastic energy. There's no thermal energy. But I've lifted it up, haven't I? Sure have. So there's some gravitational potential energy there. There is. Now, if you would have looked at this when you were doing the 5.2 stuff, you'd be like, that doesn't make any sense. You got no bars at the beginning, you got 3 at the end. What's up with that? Here's the deal. This is not a closed system anymore, is it? No, it isn't. We have got an outside force, this hand lifting up on this cheeseburger. So now, here's the thing we have to add. This is new stuff right here. We're going to add an arrow in that says that work is done. How much? Well, it's 3 bars. And what's it coming from? It's an applied force that is giving that system some more energy. Okay, so now we're kind of broadening the scope of our bar charts from just having it the same at the beginning and the end to now we can do work. We can actually get stuff done and change the amount of energy in the system. Hot diggity, it's pretty cool. I want to look at one more thing. This is pretty awesome, you guys. Okay, so take a look at this other way to kind of look at this whole system. Okay, we're saying it is not a closed system. Okay, and as a result, that applied force is causing the gravitational potential energy to increase. Okay, so we could write out our conservation of energy statement or our energy transition statement as we've got the initial energy, which was 0, plus the work that's been done equals the final energy. You can call those A and B. You can call them whatever you want. So I've got mg h initial. We called that 0, but you could call it whatever you want, plus the applied force, that's Fa, times that change in position, that d, or really it's like a change in height, is equal to mgh final. How are we doing so far? Is that making sense? We said that this Fa is really mg, right? It's the weight of the cheeseburger. So these mg's are going to go away. Hold on to your hats, you guys. Mg's are going to go away. And really what this is saying is that the initial height plus a change in height gives you the final height. This is not magic. This is just physics. It's right there waiting for you right here. Okay, from this, we can write down one more super important thing. Here it comes. Oops, let me see if I can scroll down a little bit so I get a little more space. Can I? No? There we go. We can say, here it is, this new concept called the work energy theorem. I feel like having this in such a little tiny corner is not doing it. It's not selling it. So I'm going to move this down and give myself some more space. Okay, here's the game. In an open system, non-closed system, the work done is equal to the change in energy of the system. Bam, right there. This seems kind of trivial, but friends, it's one of the most important things that we can say. All right, check out the next video for a couple more examples and one more definition. Thanks.